Right, welcome everyone. So our next speaker is Dodd from University of Groningen. I know I'm not pronouncing that correctly. She's a PhD student there, had her master's degree from Lancaster University, and working on, let's say, broad topic of galactic archaeology. Welcome, Emma. Thank you very much for being here, actually, and have a nice talk. Thanks.
Thank you. Thanks. I'll share my screen now. I also can't pronounce Groningen correctly either, so don't worry. But yeah, so hi everyone, and good morning from the Netherlands. So yeah, I'm a second-year PhD student here at Captain Institute in Groningen in the Netherlands. And today I'm going to talk to you a bit about some work that my group have been doing. So looking at substructure in the local stellar halo, and this is based on mainly two papers. So that the first two that you see here, so Lovedahl et al. 2022 and Ruslara et al. 2022, and it's a team of 5 or 6 of us from here at Captain working on trying to figure out a bit more about the accretion history of the Milky Way. So I'll dive right in. And we know that our galaxy, the Milky Way, has had an accretion history because of observations and also from theory and simulations. And we know that through lambda CDM cosmology that galaxies are formed hierarchically and build up to the galaxies that we see today at redshift 0. And our Milky Way is no exception to this. And the image that you see here is just a artist impression of the Milky Way, but just to kind of give you an idea that when you go out of the disk, we enter what we call the galactic halo. And as well as a dark matter halo, we also see a stellar halo. And we see a lot of these beautiful stellar streams that form in this halo. And we get these thin streams that form from star clusters like globular clusters as they're disrupted. And also we get these streams from small dwarf galaxies as they're accreted. So you can imagine that this is like the nucleus of the leftover dwarf galaxy that got a bit too close to the Milky Way, and then the stars get stripped in these leading and trailing streams that follow the orbit that galaxy is on. And so we can look for these streams to learn about the accretion history of the Milky Way. And now I will show you, I'll show you some real data. So this is with Gaia, which I'll tell you a bit more about shortly. But this is a team that used Gaia data and combined it with an algorithm called Stream Finder to try and find a lot of these thin streams in the Milky Way's halo. So the background image that you see here is actually real data from Gaia, and then binned and given a color according to the mean color in that region. So you get these beautiful images of the Milky Way. And then we also are able to detect a lot of streams and substructure in the halo. And some of these streams, like for example, PAL5, will have formed from globular clusters, but some of them, the ones that have a higher velocity dispersion and a higher metallicity dispersion, probably formed from dwarf galaxies that were accreted, very small dwarf galaxies. So our job is to try and find these streams and then characterize these streams. But the picture gets even more complicated when you look at more massive dwarf galaxies. So now, now I'm showing you a model of the Sagittarius dwarf galaxy. So this was discovered back in 1994, and there is a remnant of a dwarf galaxy that you see in the Sagittarius constellation when you look from our point at the sun. And this gives us one of the best evidence for the accretion history of the Milky Way, because we can see this merger that is ongoing today. And we can see these beautiful streams that stretch out and wrap around the galaxy multiple times. And these streams are actually quite complicated. We have substructure and multiple wraps, and they go very far out in the halo that we're still struggling to kind of reach that region and get distances for stars that far away. But we have a lot of models and a lot of observations of Sagittarius and the streams to be able to kind of get this picture that we have today. And it gets even more complicated than this. So if you have a galaxy that was accreted earlier on, or a more massive galaxy, then the debris gets deposited into the inner halo, and we get something that looks like what I'm going to show you now in this video on the right. So the red are a small dwarf galaxy, but still relatively massive, that's on an orbit that brings it close to the inner halo, and the white are the stars in a Milky Way-like galaxy. And you see that a stream starts to form and wraps around the galaxy as these stars are stripped from the dwarf galaxy. But quite quickly, the stars spread out along the orbit, and soon you'll be able to see that we can no longer find that the debris from that galaxy as streams on the sky, and we actually have to look at other properties. And if you look in a small volume, we see that the stars are kind of moving with the same velocities and still moving along the same orbit, but just very spread out along that orbit. And we call this phase mix debris. So it's no longer spatially coherent, but it's still coherent in velocities in a small volume, and also in properties that we call integrals of motion that remain conserved along the full orbit with time. So since we can't look for these streams, this debris as streams on the sky, we want to use properties that remain conserved along this orbit. So this is what I'm showing you now. I'm showing you energy and angular momentum, where it's the Z component of the angular momentum. And these are two properties that we use and we refer to as integrals of motion. And the energy of a star is a true integral of motion if we can assume that the galactic potential hasn't changed over time. So not a perfect assumption, but reasonable enough for us to make. And then the angular momentum of the Z component of a star, it remains conserved with time if the galaxy is axisymmetric. So we can make this assumption for the Milky Way that it's symmetric above and below the disk. And then we can also use this as another property that is conserved. And what I'm showing here is some simulations of different satellite galaxies. So here each color is a different galaxy. So this is one galaxy, and this is another, and some of the colors are repeated. So this is also a different galaxy. And these galaxies are in a Milky Way-like potential, and they're about to be disrupted. But you can see that the stars form clumps in this space. So a galaxy has a mean energy and angular momentum that tells you the orbit that it's on, and then it has some spread associated to that for the individual stars that corresponds to roughly the size or the mass of the galaxy, but also corresponds to the orbit that they're on. So things get more spread out when you go to lower energy, and it's a bit more difficult to disentangle things. But this is an initial distribution. But if we let these stars and these galaxies disrupt in the Milky Way and fully mix within the Milky Way, then what does it look like in this space? And that's what you should be able to see now on the right. So this is after 12 gigayears, which is a very long time, of these galaxies fully mixing into the Milky Way. So we no longer see them as these streams on the sky, but we can see that the clumps and the substructure in this integral of motion space remains conserved. And so we can look for debris in our own Milky Way by looking for over-densities like this in this energy angular momentum space. And so to do this, we need 60 phase space information for the stars. So we need the position on the sky, the proper motion, the distance, and the line of sight velocity, which can be quite difficult to obtain for many stars, and especially stars that are further away. But for this, we use Gaia data. So Gaia was a mission, not yet. Gaia is an ESA mission that was launched in 2013, and it's scanning the Milky Way sky and getting us a lot of information on a lot of stars. And it's on its third data release. So in June, we will have data release 3, but we already had an early data release in December of 2020. And that's what this work that I'm presenting is based on. We have 1.8 billion stars that have a position on the sky. and 1.4 billion that have a parallax and a proper motion, and then 7 million where we have a radial velocity or line of sight velocity. So that's a lot of stars, but unfortunately, the parallaxes can't be trusted for all of that 1.4 billion stars. So to get the distances, we invert the parallaxes, but we can only do that for the stars that have a very small parallax error. Otherwise, it just goes too crazy. So then we're limited to a very small volume, actually. So the volume that we're limited to, you can see here. So the background shows like an artist's impression of the Milky Way, and then the red circle shows 2.5 kiloparsecs volume around the sun, which is the volume that we're using in our study, where we can trust the parallaxes to get the distances, and then we take all the stars in this volume that have this 60 information, but we also extend the sample slightly. So instead of just using stars that have radial velocities from Gaia, we also use stars that have radial velocities from these ground-based spectroscopic surveys, so Apogee, Galar, Lamost, and Rave. And this gives us a sample of around 51,000 stars that we call our halo sample. And we select the halo by making a kinematical selection. So we select stars that move on halo-like orbits. So they move differently to the disk like stars. And we're a bit conservative in that cut, so that we do still have some disk contamination, but we want to have as many halo stars as possible. So that sample looks like this when we plot it in integral of motion space. So you see here, this is the energy that I was talking about earlier. This is the Z component of the angular momentum. And then this third component is this L perp or L perpendicular, which is the other component of the angular momentum. So in total, L perp and LZ make up our total angular momentum. And the perpendicular angular momentum is not a true integral of motion, at least not for unless you have a perfectly spherical galaxy. But we know from simulations and modeling that stars should remain clumped in this space, even if it's not perfectly conserved. So this is the 3D space that we want to use to try and look for these over-densities and look for substructure from different merger events that might have deposited stars into the local halo. And to look for these over-densities, we use a clustering algorithm, and we actually tried to go as basic as possible in the first place and develop our own kind of algorithm to do this, because we wanted to have maximum control. We didn't want to be setting certain parameters to certain things and not have a feel of what that was doing. And we also didn't want to be making assumptions about the shape of a cluster, or at least not as little as possible at this point. So we use just a simple single linkage algorithm as a basis. And the idea is that if you, here is just like a 2D example of this, where at each step of the algorithm, it links the two closest points until the final step where every star or point is linked together. And then you have to figure out where you want to read off on this tree, where you want to take your clusters and which clusters are significant. So to do that, we used a random halo set. So this is what you see now on the right. So you see at the top, the Gaia EDR3, my halo sample in energy in LZ. And at the bottom, you see one of our random halo sets, which were created by randomly shuffling two components of the velocities so that you get a smooth halo, and it removes these correlations between the velocities and removes the substructure. And you can see actually that things like this little overdensity here is not in the random halo set. And we make 100 of these random ones, and we use the averages of these to look at how many stars are within the two. So for example, if this was in our halo set and this was a cluster, at this step, it would fit an ellipsoid around these 4 stars. it would count the number of stars that fall within this ellipsoid in the real data, and how many fall within this ellipsoid in the random halo set. And this would give us a measure of our significance. And then what we do is we extract the clusters when they reach their maximum significance. Maybe at this point, it is most significance for the stars to be in 2 clusters where 1 and 2 are joined and 4 and 3 are joined. But when you join the 2 together, it becomes less significant. And so we would take them at this point rather than this point. And anyway, in the end, we end up with 67 clusters that have significance greater than 3 sigma. And this is just showing them in this integral of motion space, where a different color is a different cluster, and stars of the same color are from the same clusters. But you can see that there is a lot of overlap between the different clusters, and we don't expect that there are 67 merger events that have populated the inner halo. So then we have the job of trying to then link these together and see which clusters are related. But we can also look at other properties like the velocities. You can see now on the bottom the same clusters are colored by which cluster they're in, but in velocity space. And we use this actually to look for individual streams. So if you have a phase mix dwarf galaxy going through the inner halo, you expect there to be individual smaller streams within that. And so we can look for substructure within the velocity space to find this. And we can also look for interesting clusters. So those that are those that are very, what's the word? Very compact, I guess, in velocity space, might be hinting at a disrupted star cluster where it's a very thin stream, and so the velocities are very, very coherent. So that's also something that we look at. But the rest of this I'll tell you about linking our different clusters together. So linking the clusters together, we start with a very simple kind of approach of just which clusters are close in this integral of motion space. And to quantify that, we use a Malahonobis distance between each cluster and the other cluster distributions. And this is basically a way of comparing how close they are without just taking into account the means, but also taking into account the sizes of the clusters and the spreads and the orientations of the clusters. And then we do another single linkage just to link these clusters based on these distances, and you end up with something like this that you see the dendrogram at the bottom, where we've taken a cut at a distance of 4, which is fairly arbitrary and not our final result, but just a starting point. And you end up with these 6 main groups in the halo, and a few extra clusters that are left unlinked with other clusters. And the reason that we take this cut of 4 is mainly to make sure that we are seeing what previous studies have seen. So previous studies have associated the debris in this region to one merger event called Sequoia, the debris in this region to one called Gaia Enceladus, which is the most massive merger thought to be the most massive merger that the Milky Way has experienced. And then this region down here is thought to relate to a structure called Thamnos. E is thought to be the Helmi streams. A is actually in situ, so we don't think this is a merger. We think this is a disk-like structure. And then F is something else that we're not sure what it is at the moment. But this was just a starting point to see how these clusters link. And this was the first paper, but the second paper is going into more detail to try and link these different clusters by using the stellar populations in the clusters, so that we can say a bit more about how many mergers have contributed to the local halo. So in paper 2, we use these stellar populations, and this is just one example, which is the Helmi streams. So this is a accretion event that's been studied a lot since it was discovered in 1999. So it's a good one to test that the stars in the two clusters are the Helmi streams. So in previous studies, the stars in this region have been attributed to just one merger event. And the clustering algorithm picks up two clusters that you see in these two different shades of green. But when you look at their color magnitude diagrams and also their metallicities that you see on the right here, you can see that they're very consistent with being the same stellar populations. And so we can use the fact that they are very close in this integral of motion space and that they have the same stellar populations to link these two clusters together into one structure that we call then the Helmi streams. And this is just, one example, but the second paper outlines the procedure of how this is done using statistical things like KS tests to do this properly, but I won't go into that detail now. I just wanted to highlight that this is what we're doing. And as well as the metallicities and the color magnitude diagrams of the stars in the clusters, we also use chemical abundances when they're available, but that's a lot more limited for our sample. But when we put all of this together, we end up with something that looks like this. So you see this energy LZ plot again. And now we see that there are not just 6 groups. After linking clusters more robustly and using the stellar populations, we end up with around 12 substructures that make up our inner halo. And I will just go through quickly these. So we have, first of all, Gaia Enceladus. So we find that there is a lot of clusters in this region that we link together into one structure that corresponds to this Gaia Enceladus merger that's been found previously. And then we have this second little cluster, cluster 6 at the bottom, that we separate out from Gaia Enceladus because of its metallicities. So in the red box on the right here, you can see Gaia Enceladus's metallicity distribution, and you can see then in the panel for cluster 6 that they don't follow each other exactly the same. So cluster 6 actually peaks at slightly higher metallicity and doesn't have as many metal pore stars as Gaia Enceladus. So our procedure for linking clusters suggests that the two would be different. But we are not sure fully what cluster 6 is, because it's a very small cluster but quite metal rich, which doesn't make sense because of the mass metallicity relation of galaxies. If it's more metal rich, then it should be larger or more massive. And so we need to look into this a bit more and figure out what's going on here. Maybe it's just part of Gaia Enceladus that is contaminated by disk stars because it's lower energy, or maybe it's telling us something about the center of Gaia Enceladus. Maybe the nucleus of Gaia Enceladus is at the bottom, which would make sense due to dynamical friction, that those stars that are lost at the end of the merger sink to lower energy. But we need more work to see this. Then we have Famnos 1 and 2. So these were 2 dwarf galaxies. Well, we think these are 2 dwarf galaxies that were found in previous studies, but the results of our clustering algorithm, when we look at the 3 clusters that were in this space, 2 of them seem to agree quite well with each other, and one of them has slightly different integrals of motion, as well as slightly different metallicities. But it's a lower number of stars, so I guess again also more work is needed to know whether these are different. Then we have the Sequoia region. So previously this has been thought to be just the debris from one merger, but we actually split it up into the 3 clusters in that region. So we think that actually only one of the clusters out of the 3 that we find in this region correspond to what people call Sequoia. And this is because of the kinematics, which I'm not showing here, but they have slightly different kinematics. They also have slightly different metallicities, but not so different. But the fact that this spread in this energy in LZ is so huge, means that also motivates why we want to split them into three, because if the galaxy was, if it was one merger event, it would have to be much more metal rich because of this mass metallicity relation that I was talking about. For it to take up that much space, it would have to be a very massive merger. But the metallicity suggests that it is not so massive. So that's one reason why we do that. But we don't know what 64 and 62 are yet. We will have to see. And then we have the Helmi streams that I just showed you before. This one is made up of the two clusters that we found and consistent with other studies that have looked at the Helmi streams. We also have this cluster 3 down at the bottom in low energy. And it's very difficult to kind of find these things at low energy because of how dense it is in that region and how contaminated it will be. So you see that we have this very high metallicity peak. So this is a big contamination from disk-like stars that have been heated onto halo-like orbits. But we do have quite a substantial metal poor population. So maybe cluster 3 is a mix of an accreted population and a more in situ, so stars born in the Milky Way. But again, we have to see. And then we have this region of A, which we believe is the thick disk, the thick disk stars that have been heated into halo-like orbits. So this ancient thick disk. And then we have 38 and 12 that are also on disk-like orbits, but especially 12 has some contamination from metal poor stars. So we again have to see what this is made up of. And I said that we used chemical abundances where possible, and the importance of chemical abundances is that galaxies of different masses and also that formed at different times will have different tracks in this alpha over iron versus iron over hydrogen space. And so we looked at these as well, but as you can see, there are not many stars that we have these abundances for just yet. But the idea is that the accreted population should fall on or around this low alpha branch, and then the more in situ stars that were born in the Milky Way will fall on this high alpha branch. And so what you see here is that the structures A and 12 and 38 that we said were disk-like do fall on this branch, and then Gaia Enceladus falls on this low alpha branch. And then cluster 3, the large one at low energy, seems to be a mix of the two populations. But we can follow up, and hopefully in the future we'll have a lot more chemical abundances, and then we can even get the trends of individual galaxies and really determine differences between, for example, the Helmi streams and Gaia Enceladus. But we will see. I guess the other things is that we see some trends in the local halo. So I said that we used color magnitude diagrams, and we fit isochrones to these color magnitude diagrams for each structure. And then you see here the structures. So Gaia Enceladus, Thamnos 1 and 2, colored by their average age. And we seem to see that more retrograde structures, so those that are orbiting in the opposite sense to the disk, most likely to be accreted because of this opposite rotation. They appear to be older than the prograde structures, and they also appear to be more metal poor. But since some of these are mixes of populations like cluster 3, and some of these are we think are the ancient disk, we have to do more work to kind of understand what these trends are telling us. But maybe they tell us about which groups fell in which times, whether there was a group infall. So if we see a lot of structures on similar orbits with similar ages and metallicities, maybe they fell in together and not just one accretion event at a time. But for the last couple of minutes, I will just talk a little bit about the dynamics of just the one structure, so the Helmi streams. I told you that the Helmi streams is made up of these two clusters that we put together into the one structure, the Helmi streams, based on the fact that they had the same stellar populations. But this is something that we saw actually before we ran the clustering algorithm. So it's nice to see that it gets reproduced in both methods. So when Gaia EDR3 first came out, we went to reselect the Helmi stream stars in this angular momentum space that is commonly used. And we used to use these dashed box selections that you see here. But when we looked at Gaia EDR3, we saw that the stars don't really follow this box or a one clump like shape, but actually seem to be two clumps of stars. And so what we did before running the clustering algorithm was we just selected the two clumps by eye based on the fact that we see this gap and we see these two over-densities. And we wanted to check whether the stars in both of these clumps were both Helmi streams. I already showed you some cool magnitude diagrams and some metallicities distributions for the two clumps from the clustering algorithm, but we saw the same before when we just selected the clumps by eye. But we wanted to understand what causes this substructure. So since the two groups have the same stellar populations, they should just form one overdensity in this integral of motion space. So why do we see this gap, and why do we see this separation into two populations? And so for this, we had to look at the dynamics and figure out what this is telling us. And so we look at the orbital frequencies here, which basically tell you how a star is oscillating above and below the disk and how it's oscillating around the galactic center. And if you color these frequencies by which clump the stars are in, you can see that the stars in the higher angular momentum clump, so the red stars, seem to have different frequencies from the stars in the lower angular momentum clump, the blue stars. So this means they're on slightly different orbits. And the fact that this distribution of the frequencies is narrower and more peaked means that the stars are on even more similar orbits than the blue stars are, if that makes sense. And we think that they are actually on a resonance, and that this resonance is the reason that we see this substructure. So this is not related to the accretion, but actually related to the galactic potential of the Milky Way. And so we can use these accretion events and the substructure in these accretion events to learn about our own potential. But it's also a problem because it's complicating our identification of these accretion events. So because the one clump is splitting into multiple, then we have to do the job of finding them, linking them together. But then, as I said, it's a positive to learn about our galactic potential, because that's something we also need to know to do the job that we do. So we actually used the Helmi streams and this substructure to try and constrain the potential, because I showed you in that frequency histogram on the last slide that we think these are on a resonance, but they're not quite on this 1-1 resonance that you see by the dashed line in the two plots. And it's much more natural for the stars to be on this 1-1 resonance, and maybe not the definitely true, but it makes sense that if we get the right galactic potential, then the stars could possibly lie on this 1-1 resonance. And so what we did was we varied the model of the galactic potential that we were using, and recalculated these frequencies, because to calculate the frequencies we have to integrate the orbits in a galactic potential. So we changed the shape of the dark matter halo component in a commonly used Milky Way potential, Macmillan 2017, and we just changed the shape and see how these frequencies change. And you can see that as we
I guess your microphone is off.
Pardon, sorry?
Your microphone went off for a second, I guess.
Oh, you can hear me now?
Yes, yes. Fine.
Okay, sorry. It might be my internet. Apologies for that. So I don't know if you missed anything, but I guess I was just saying about how we vary the shape of the dark matter halo in the Milky Way potential and recalculate these frequencies. And as we go from a oblate shape for our dark matter halo to a prolate shape, these frequencies change, and at one point we actually find that they lie on this one-to-one resonance, which suggests that this shape for the dark matter halo could be the true shape. And another thing that we can check is we can look at how the angular momentum of these stars evolves with time. So the angular momentum doesn't depend on the galactic potential. Integrating the orbits does, so we have to use a model, but calculating the angular momentum today doesn't depend on this potential. But then if we integrate the orbits and recalculate the angular momentum, then that depends on our potential. And we wanted to check that if we assume we're not in a special time right now and that these clumps should be long lasting, then if we integrate the orbits in our potential with a shape of 1.2, an axis ratio, then do the clumps remain or do they mix together, and is this substructure destroyed? And we find that actually for this potential where the stars are on this resonance, we also find that it's the least amount of mixing in this space, and the clumps are long-lived. And so, so we think that this suggests that the shape of our dark matter halo is slightly prolate with an axis ratio of 1.2, and this agrees actually with some other studies that have probed the similar regions, and this is just probing the inner galactic inner dark matter halo, but it gives us an extra measurement, which is quite nice. And then I will go to my summary. So thank you for listening, and everyone who's still with me. So what we've done is we've developed a clustering algorithm to try and find the merger debris in this integral of motion space. And we find that there are around 12 structures, many of which were already identified, and some new structures that need some more work to understand what kind of populations they are, whether they're a mix of two, or whether we're seeing something new. And around 20% of the halo can be attributed to these substructures when we link all the clusters together and add stars that are in those regions. We get around 20% of the halo in these structures, but not all of this is accreted. And we saw some trends in the local halo, and which are older and which are more metal poor. And then we also demonstrate that we can use these accretion events to learn more about our galactic potential. So that's all from me. Thank you very much for listening, and I'd be happy to take any questions.
Thank you very much, Emma. Are there any questions, or Kai, go ahead.
Okay, very nice talk.
Thank you.
I'm sorry if you talked about this, because in between I had some technical problems. Maybe I missed it. I have two questions regarding what happened very early and in the end. So the first one would be, I mean, if these dwarfs are captured and form this stream stand, I guess in the end they merge with the Milky Way due to friction with the disk, and somehow in the end just move with the rest. Do you have any idea what time scale that would be? How long that takes? I guess probably that depends on the size of that dwarf galaxy. But is there any, I don't know, rough estimate that one would get from this?
Yeah, I don't know off the top of my head roughly what time scale, but it depends definitely on the orbit that you're on. So, for example, if I go up here, so the Sagittarius is thought to have been accreted around 8 gig years ago, 6 to 8 gig years ago, I believe, off the top of my head. But we still see that it's still being stripped. Whereas this video that I showed, I don't know if you saw this, but this is a model for the Helmi streams, which was accreted maybe around 8 to 10 gig years ago, but these kind of estimates are still, we still need to iron them out a bit better. But because this accretion event is in the inner halo, the orbital timescales are a lot smaller. So it in the same time it orbits the Milky Way many more times, and so it gets mixed and fully disrupted a lot faster. So these are, I guess, similar kind of timescales, but you end up with a picture like this for a galaxy that was that entered the inner regions of the galaxy, whereas if the dwarf stays in the outer regions, you see that it's not fully disrupted even after maybe 6 gig years.
Okay.
Yeah.
That's long. And another quick question: say, is it clear where they come from? Are they kind of captured? Say they move through the universe, and at some point they're captured by the Milky Way, or could they even be formed together when, I don't know, the Milky Way formed?
Yeah, it's a good question. I guess we don't really know yet fully. I guess the earliest accretion events could have been subhalos or of the Milky Way that formed with the Milky Way, and others could have been captured. But for now, I guess we're not so sure. We're still trying to, I guess, find the debris from these, and then hopefully we can figure this out. But I guess it's very hard to model, because we think that some of these galaxies could have fallen in together as well. Like some of them could be satellites of each other, but it's just very hard to disentangle this all at the moment.
Okay, thanks so much.
Thanks.
Any other questions? Or Seda, go ahead, please.
Can you hear me?
Yeah.
Hi, Emma. A very nice talk. Thank you for that. So it's not your outline talk, but I'm wondering for the chemical abundances. So do you have any sodium line, or just you checked the magnesium line for that?
I think some stars do have sodium, yeah, but we haven't looked at it for this specific study. But one of my colleagues is the one who's the expert or in charge of the sodium lines. Sorry, the chemical abundance side of things. But yeah, I think some stars do have sodium, but I'm not sure the numbers of how many. But it would be very good, I guess, to look into this, especially because.
Because I'm working on the dwarf elliptical galaxies, especially outside the local group. So they are not resolved stellar population, but I'm very wondering because we found a very unusual behavior for the sodium. So I want to ask, do you have any plan for the other elements to look for?
Yeah, okay, thank you. Yeah, so I think Matsuno Tadafumi, the second author of this paper, he is doing a lot with the chemical abundances. So not so far these structures that we found, but previous work he's followed up with abundances. So I think there will be a plan to look into this different abundances in the future, but I'm not sure how near future. But
yeah, thank you very much.
Thank you.
Any other questions? Sharon, go ahead, please.
Okay. Hello.
Hi.
Thank you very much for a very interesting talk. I missed the beginning part of it, but I think I caught up a bit. So I'm curious about just one thing here that I perhaps thought you could extrapolate a bit, elaborate on it. These structures that have these retrograde orbits and retrograde motion in the halo, basically, right? If I understand this correctly, is part of the halo. And how do they form actually? What is this the concept of retrograde motion in the halo? Is something well known, or this is something very new, or how does that reconcile into the motion actually, or is it something extremely small? like the motion velocity or something is extremely small, or usually whatever is moving in the halo, right, is pretty fast. Well, yeah, pretty fast, let's say. And so they're retrograde. And how do they acquire that? I mean, what could cause that a retrograde motion in the sense? Can you explain that?
Yeah. So I think all of the retrograde structures will be accreted structures, I believe, or maybe not, I'm not so sure now. Actually, now that I'm saying it out loud, but the idea is that I guess the disk moves in one direction, but when you go into the halo, the motions are a lot more random. So we have a lot the stars moving in different directions. So they're not rotating, so to say, in the same plane as the disk, but they're moving at least in the opposite sense to the disk, but maybe on more elliptical orbits that bring them far out and bring them back in.
That's right.
But yeah, so I think I guess now I'm thinking about it, and now I'm not so sure, but I was thinking that so all the retrograde stars should have been accreted because they otherwise how would they get this motion that is opposite?
Yeah, that's what this was a little astonishing for me too. So I was just thinking, because I had read some time ago that actually the halo, our halo, has some basic it has basically a spin in a way. It's it's rotating with a given velocity, right? So am I right or wrong? Am I making this up? But I remember that there's some hot maybe it's a hot warm halo or something like that has some certain rotation. This is what I had heard. Maybe I'm wrong, but I'm
not so sure.
Okay. Then so I'm just assuming that I was just thinking that since we have this in the halo structure, okay, individual material in it is basically plunging in and out as faster, and okay, whatever is accreted perhaps could have some retrograde motion, but then I don't know how that would reconcile in the general kinematics in that way, but I probably have to think about this myself to try to understand that. And okay, so and just one other thing, and how that does that, for example, does that have any effect on that prolate structure you see? You basically found that the halo structure is not oblate but prolate, right?
Yeah.
This is something very interesting. So is this something also? I'm not an extragalactic astronomer in that sense. So if that was something was perhaps found and firmly before, and that's extremely interesting. Perhaps that has to do with anything with this retrograde behavior.
Yeah, so the prolate shape is of the dark matter halo, but I guess I'm not so sure what shape the stellar halo would have. There are studies that have looked into this and tried to quantify that, but for example,
have a different sort of stellar halo shape and a different dark matter halo shape. That's very interesting.
Yeah,
but anyway,
we think so.
I don't want to confuse you with my questions anyway.
We think so.
I thought that was very interesting. I hadn't seen that before, this prolate behavior in the dark matter halo. That's very, very interesting. So
thank you. Yeah, thank you. Yeah, so I think we think that
but that, to my understanding, if I'm my small understanding, not so deep understanding, but that should definitely have effect on the stellar structure, or that the halo shape in a way. I can't imagine having a dark matter halo which is prolate with a very oblate stellar halo shape. That they should basically then, for example, what I would think then you could cause some certain way of precessional rotation or something if that happens. Anyway, forget it. That's very interesting though. That was very impressive. Very impressive. Thank you.
Thank you very much. Yeah.
Thanks a lot. Emma, I had a very quick question actually to ask. This shape of the dark matter halo, does that have anything to say about the density profiles, like this NFW profiles and so on, or is it just the same density of the dark matter but with a different shape? Does that?
Yeah. So for this one, we just use the same density, but with a different shape. Yeah. Yeah. Right. But there are other things that we could try. So we use the NFW density, but there are other things we could try, and we think actually that the shape varies. So this is just one constraint on a small region of the inner halo where the Helmi streams enter, but people think that it changes with height above the disk. So it goes from a more oblate to then a bit more prolate, and then maybe spherical. I don't know. There are lots of constraints at different radii. So I guess we'll see what picture we can put together in the end.
So just one maybe final question. Like in total, you found, I don't know, like about 10, let's say 6 streams within this region that you said we were sensitive enough, like about 2.5 kiloparsecs around the sun.
Yeah.
What does that tell us? I mean, when we look at the, let's say, evolution of spiral galaxies in general, like how many such streams would have happened in the past, like in total? Does that tell us anything about that? I mean, do we have a limit or anything?
Yeah. So I guess there will be a lot of there will be mergers that maybe have happened that won't enter this volume, and then we can't say anything about them. So there's one called Kraken that has been found and that populates the very inner galaxy that we can't find because of our volume. And also the debris that goes further out, like Sagittarius, that also doesn't enter our local halo, or at least not enough for us to detect it. So yeah, it gives us an idea, I guess, of only the local halo, but we expect that a lot of these big mergers and these early on mergers will be phase mixed enough within the galaxy that we should expect them to pass through this local region. So we think we have a decent idea, I guess, of the main, especially when you combine that we know about Sagittarius and we know about this Kraken. I think we have a decent idea of the main building blocks, but these smaller mergers that are further out, we definitely miss. So the total number, I'm not so sure, but a lower limit of yeah, I wouldn't like to put a number on it, but I guess at least a handful, maybe more.
All right. Thank you very much. So
Thank
if
you.
there are no other questions, is there one in chat? Okay, there's one question. Let me just very quickly ask. Is it possible to measure the quantity of dark matter in the dark matter halo?
I guess so, but I'm not so sure how we would do it. I guess, I mean, we can vary the mass of our dark matter halo, and then we would kind of get a measure for that and see how that changes things. But we didn't do that ourselves. We only changed the shape for now, but it would be something we could try in the future. Yeah.
All right. Well, Emma, thank you very much for your time.
Thank you
for this very good talk, very nice talk. Wish you the best of success in the future. Thanks.
Thank you very much. Thank you for having me.
Bye, Eva.
See you. Have a nice rest of the day.
You too.